So hello, welcome to my channel. So in this video I'm going to derive the circuit response equation of the parallelly connected RLC circuit in frequency domain. So in my previous video I derived the equation of this same parallel RLC circuit, which is source free, in time domain. So I'm gonna do the exact derivation but in frequency domain. Okay, so let's get started without any delay. So you can see that I have done the Laplace transformation of this LTI system. So we know that if a system is linear and time invariant, we can apply the Laplace transformation. So by which we can analyze a system in complex frequency. Okay, so in its complex frequency domain. So because we can apply Laplace transform on an LTI system, we can analyze that system in frequency domain. So I have transformed this circuit in time domain to a circuit in frequency domain. So the transformed inductance, so here is SL, so this is 1 by SC. So I have used the current source analogy for the assumed initial current through the inductor and initial voltage across the capacitor. So after the Laplace transform, the the circuit or this system of RL and C with initial conditions look like this. So in time domain, this RLC circuit as an entire system generated a second order differential equation, linear differential equation with constant coefficients. Now after the Laplace transform in complex frequency domain, this transformed circuit of the parallel RLC circuit will generate an algebraic equation. Okay, so because this is also a linear system in frequency domain, we will use KCL. And as before, because now in frequency domain the equation will be algebraic, so the calculation will be very easy. So this common point as ground, so at node A, so here I have assumed node A. So by KCL, so I have assumed current through the inductor, resistor and capacitor and the corresponding current sources. So it will look like, so incoming outgoing currents are IR plus IL plus IC. So these are all in Laplace domain, and the incoming current are, so incoming current, there is only one current, this current source is incoming to the node, so CVO minus, this is outgoing actually, so IO by S. So now, so current through the resistor is V, which V, the node voltage, which is in Laplace domain or complex frequency domain, which is S domain, by R. R is not function of frequency S, so R is R, no change there. And current through the inductor is the node voltage, which is in complex frequency domain, by SL. So 1 by SL is the inductive susceptance. Okay, so because we are applying the node voltage formula, now IC in current through the capacitor is SC Vs. SC is capacity susceptance. Now let me write this. So if I take the common Vs out, it will, so if I take C by S common from this, it will look like S square plus. Now what I'm gonna do is, so S square plus 1 by RCS plus 1 by LC, the node voltage. So now this becomes, so SVO. So taking this C by S to the right hand side will make the right hand side SVO minus IO by C. So before I do the division in this side, so I want to break this second order term into, I want to factorize this basically. So how am I gonna do it? So S square plus 1 by RCS plus 1 by LC, say this is equals to S minus lambda. I'm gonna equate the coefficients. So by equating, it will give me lambda 1 plus lambda 2. So if I let me, so lambda 1 plus lambda 2 is minus 1 by RC, and lambda 1 lambda 2 is 1 by LC. So to get the individual lambda 1 and lambda 2, let me write formula. Now lambda 1 minus lambda 2 is root over, so lambda 1 plus lambda 2 whole square, lambda 1 plus lambda 2 is minus 1 by RC whole square minus 4, lambda 1 dot lambda 2 is 1 by LC. If I define damping factor here, which is 1 by 2 RC, and undamped natural frequency omega n is 1 by root LC, so it will give me it will easily give me, so 4 1 by 2 RC. So there's no meaning for this minus, because we have squared it, the minus will vanish. So this 4 1 by LC basically. Now if I take 4 out, so 2 root over zeta square minus omega n squared, and here omega d is the damped natural frequency, which is omega n square minus psi or zeta square. So here it will be 2j omega d. So far so good. Now we are gonna find the individual lambda 1 and lambda 2. Now by simple arithmetic, I will get lambda 1 equals to minus psi plus j omega d, and lambda 2 is minus psi minus j omega d. So we have found our roots to factorize this second order term. Now what I'm going to do is I'm going to use these roots and find the answer. So I have written all my assumed and all my calculated terms here, and now what I'm going to do is, so here V is node voltage in frequency domain, the complex S domain or Laplace domain is, so here SVO by s square plus 2 psi s plus omega n squared s plus omega n squared. Now I'm just gonna factorize this. So VO, so so I'm gonna write this in factorized form now. So s by s minus lambda 1 into s minus lambda 2 minus, so IO by C 1 by s minus lambda 1 s minus lambda 2. So far so good. Now what I'm gonna do is I'm gonna break this. So I'm gonna break this term into partial fractions. So say VO, this is a by s minus lambda 1 plus b by s minus lambda 2. So all I have to do is find this a, b, c, so a, b, d and e. So these are arbitrary terms, so I have to find these. So here in this case s equals, so I am equating this term by this partial fraction term. So here I'm equating this two. So if I take this and multiply on two sides, it will give me s equals to a. So if I take if I now equate the coefficients, it will give me, so a plus b equals 1, a lambda 2 plus b lambda 1 equals 0, from which I can get a equals minus b lambda 1 by lambda 2. So if I take this, so a is minus b, so b commoned out, and lambda 2 minus lambda 1 by lambda 2 is, here is 1. Now b is minus lambda 2 by lambda 1 minus lambda 2, and a as a result is plus lambda 1 by lambda 1 minus lambda 2. So now I am equating these two terms. So if I take this s minus lambda 1 into s minus lambda 2 and multiply in the two hand sides, it will give me 1 equals d into s minus lambda 2 plus e into s minus lambda 1. So the same operation as I did in my frequency domain analysis of the series RLC circuit. So this will give me 1 equals d plus e s minus d lambda 2 plus e lambda 1. So same as before, equating coefficients of s and constant, it will give me d plus e equals 0. So d equals minus e, and d lambda 2 plus e lambda 1 equals minus 1. So this minus will go to this side. So now if I substitute for d, it will be e lambda 1 minus lambda 2 equals minus 1. So E equals minus 1 by lambda 1 minus lambda 2. So D is plus 1 by lambda 1 minus lambda 2. So now we have found all our arbitrary terms. If you remember, lambda 1 minus lambda 2 is or from here lambda 1 minus lambda 2 is 2 j omega d. So I'm gonna use that fact here. So here VO minus lambda 2 by lambda 1 minus lambda 2, which is 2 j omega d. So 2 j omega d s minus lambda 2. So if you just look at here, lambda 1 minus lambda 2 is 2 j omega d. Okay, so now minus io by c. So if I take 1 by 2 j omega d common out, it will be like this, 1 by 2 j omega d. So after I apply the inverse Laplace transform, it will come to look like more of the form I have derived in the time domain analysis. So now what I'm going to do is I'm going to apply inverse Laplace transform on the node voltage, which is in the S domain, complex frequency domain. It will give me node voltage in time domain. Now what is gonna happen is, so 1 by 2 j omega d, and in the brackets initial voltage across the capacitor. So inverse Laplace transform this term will be, so lambda 1 exponential lambda 1 t minus lambda 2 to the power lambda 2t. So this is basic Laplace transform, inverse Laplace transform formula, so you can check it. So minus initial current through the inductor by capacitance e to the power lambda 1t minus e to the power lambda 2t. So now what I'm going to do is, so here if I break this lambda 1 and lambda 2 into these values, so it will look like, so e to the power lambda 1 t minus e to the power lambda 2t is, so now I'm gonna use this in this 2 j omega d. So VO, so I'm taking the e to the power minus psi t common out, so I'm writing it here, e to the power minus psi t or zeta t. Now what will happen is lambda 1 e to the power j omega dt minus lambda 2 e to the power minus j omega dt here minus io by c. This will be e to the power j omega dt minus now all I'm gonna have to do is take this 1 by 2 j omega d inside the brackets, inside these, and it will give me sine and cosine. So I hope you understand what I have done here. Now e to the power minus psi t. Now so VO inside, and so if I take psi common, minus psi common as a matter of fact, so it will give me psi by omega d. So this is what it looks like at the end. Now you can see, you can easily understand that this is sine omega dt, this is cos omega dt, and this is sine omega dt. Okay, so now inverse Laplace transform of the node voltage Vs gives the node voltage in time domain, which gives us this. And if I just write this, so exponential psi t, so initial voltage, and so this is cos omega dt, so cos omega dt, and j omega d by j omega d cuts out, so there's nothing in the coefficient, minus psi or zeta by omega d sine omega dt minus io by omega dc sine omega dt. So this is the answer. Okay, so fortunately in this case the answer I have found in the time domain analysis and answer I have got here now in the frequency domain analysis is the same. There's no plus minus change, so I am kind of happy about that. So this is the answer. Okay, so the circuit response, which is the voltage of the source free parallelly connected RLC circuit, is, so voltage equals to, so this is source free, there's no input, so there's no steady state response, there's only the transient response, so which is exponential e to the power minus psi t or zeta t, which is damping coefficient or damping factor, into VO, initial voltage across the capacitor, into cos omega dt minus psi by omega d sine omega dt. Omega d is damped natural frequency, which is root over omega n square minus psi square or zeta square. Now minus initial current IO by initial current through the inductor by omega dc, c is capacitance, sine omega dt. So after the analysis in frequency domain of the source free parallelly connected RLC circuit, I have found this response. So you can see this. So this is the response of the parallel RLC circuit when it is source free or input free. So I hope you understood my explanation. If you have any doubts or any complaints about my calculation and explanation, you can tell me. If I have done any mistakes, you can tell me. I will try to correct those mistakes. And thank you very much for watching this far. I hope you like my video. If you like it, like this video and subscribe to my channel and share my videos. Thank